Swayam Prabha. Digital India. Educated India.
The story goes like this. This is the first year chemistry course in IIT Kanpur many years ago. So the professor came in, the class has about 500 students, huge auditorium sort of a class. And then at the back end, about 10 or 20 professors sit, because they will divide these group of students into 30 students each and teach them tutorials, problems later. So the professors are attending this professor's lecture as well. Okay, this is how I have been told. So this professor comes in and says that the most important physical chemistry development in the past is the famous equation H psi is equal to E psi. He wrote this down and he started explaining that this equation was put forward by Erwin Schrödinger and so on. And the 500 students started writing, taking notes. So I'm dramatizing the whole sequence, by the way. This is not exactly how it happened, but something around this. So suddenly, at the door, about 5 or 7 sadhus, people in the saffron full suite, carrying the spear. What is it? Namma oorla vel solvada perse. Danda and spear. They just rush in and tell the professor, no, don't tell them stories. Don't tell them stories. You don't know what this is all about. You see, this is the truth. Not this. This is the truth. This is what you should tell everybody. And the students are stunned because, 6, 7 sadhus are garrowing the professor. They are surrounding him and they all have this danda close to him, and then this professor is sort of nervous. He says, okay, I know. So this is what is the sphere. Not very different from what I said. Please understand, that's also the sphere. That's all I am telling you. You see, there's a connection between what you are holding and what this is. It's the same thing. I'm also telling the danda, the sai is the truth and nothing but the truth and the whole truth, and so be it God. Okay. Idea was that. Oh, then the sadhus, all those people say, okay, fine. They all go away. Okay. So the students are stunned. They leave. And slowly the sadhus come and sit down on the back seat after removing their dresses, and they are former students. The professor actually enacted this whole thing to tell the students in the first class, you will never forget that this is the equation for the rest of your life. Okay. What he said was, India probably used a larger one and the Western society used a truncated one. Okay. Idea is that Schrödinger's equation, as many of you have seen, you will keep seeing this again and again. You won't understand it. At this point of time, I'll be very surprised if you have some thoughts about it. It's fine. It's not a question of understanding everything that we hear, understanding everything that we write down. It takes a while. In fact, the very famous statement by Heisenberg at one point of time is that in every real field of physical sciences, there are new developments, and the statement is not exactly what it is, but it's something like this. And there are new things, and as long as we don't ask the meaning of the word understand, we understand all of them. It is the fundamental interest to everybody to understand them, but don't ask for the meaning of the word. What is understand? Okay. So idea is that you hear them, you practice them, you use them in multiple contexts, and eventually you become so familiar with it that you think you know the subject, just like I'm trying to teach you something. It's not that I understood all of them, but I'm familiar with them. And I have done enough calculations and enough research around some of these things that I don't ask the fundamental question why things are the way they are. That question does not have a very significant answer in the first 10 years of science. The last 10 years of science, that should be the only question people should be asking, why things are the way they are. Then only you see the philosophy of science coming together. And then only the RSIC has an idea that, all of science is connected, whether a physicist talks about Schrodinger equation, or a chemist does, or a mechanical engineer talks about, mathematics. What is important is the concepts are all connected in one large circle, even though they look like they are all individual blobs. They are not. That's a phenomenal overlap between them. So today, what we would do is to start with something. I don't know if anybody introduced you to spectroscopy so far? Yes? Who did? Who? Rangarao? Okay, he talked about what? Solid state X-ray photoelectron spectroscopy. Did he talk about Raman spectroscopy? No. Only photoelectron spectroscopy. For the surface sciences he talked about, right? Okay. So that's one of the application, one of the fundamental branches of spectroscopy. But what is the definition of spectroscopy? Gradually. I mean, overall, if you want to define a spectroscopy as what? Spectrum of the atoms, okay, one. Spectrum of the molecules, if you want, atoms and molecules are there. Yeah, but what is a spectrum? The light emitted or absorbed by the atom or the molecule. Yes, you are getting closer to the definition. Anybody? Yeah.
The spectrum is the distribution of radiations that that is either emitted or absorbed by a sample.
Okay.
And then we study that.
Okay, but why does it happen? Yeah.
I assume when we irradiate an atom or a molecule, then its energy shifts, and when that shifts, it emits.
Okay. Still, a precise definition is something else. Yeah, we are getting there, close to that. Yeah.
So, when a body emits energy, it does so on various frequencies.
Okay.
These frequencies separate out, and that's what we call a spectrum.
No, that is in general not spectroscopy. That is, for example, black body, when you heat it to very large temperatures, it starts emitting. It becomes red and slowly it changes color, and eventually it becomes white if it doesn't decompose or if it doesn't evaporate. Then the white body essentially means it's emitting all wavelengths of light. That's not what I call a spectroscopy. Anyway, the light that comes out of it is called a spectrum. Yeah, as she said, spectrum. But spectroscopy is fundamentally the interaction of radiation with matter. That's a working definition of what spectroscopy is. Radiation falls on the matter, and something happens to the matter. The radiation interacts with the matter, and then you have a result. Either some of the radiation that fell on the matter no longer is seen, they have been absorbed, or if the radiation is, the matter may emit other radiations and so on. But the point is, it's basically the interaction of electromagnetic radiation with matter. Now, electromagnetic radiation, all of you know, consists of what? And electric and the magnetic field. So, if you draw the electric field something like this, okay, it's a sinusoidal sine wave or cosine wave, it doesn't matter. They are only phase shifted, And then this is what? Suppose this is called the electric field. Okay, this is the amplitude, and this is the direction of propagation of light or radiation. Direction of propagation. Okay. So if this is E, where is the magnetic field? Perpendicular to this direction and to this direction, both. So the magnetic field will be something like this. Something like that. So one field is oscillating like this, another field is oscillating like this, and both of them are moving in that direction. That's the direction of propagation. Now that's radiation, therefore it has E and then an B, if you want to write this as a B vector. Okay, but this is B. Okay, so E is E naught cosine some frequency. Okay, this is, you know what a wavelength is? The wavelength is this. Therefore, the number of waves that pass a given point in unit time is the frequency. Okay, number of whole waves. Suppose you put a window here, and within 1 second, how many waves, full waves pass through, that gives you the frequency. And the number of waves in 1 unit length is called the wave number. Okay, and I told you the relation between the two is the velocity of light, speed of light. Okay. Now, what is interesting is, this is an oscillating electric field, it's an oscillating magnetic field, so it's time dependent. Okay, the field is time, cosine omega t. Omega is the angular frequency if you wish to. Okay, omega is angular frequency is 2 pi times the nu, which is the linear frequency. But the point is the field is time dependent. That's very important. So if you shine light or radiation, light is only the visible form of electromagnetic radiation. Electromagnetic radiation ranges over 20 to 22 orders of magnitude in frequencies, starting from radio waves, okay, what are called the meter waves. Okay, the wavelength is of the order of meters, 100 meters and things like that. Radio waves to cosmic rays, which is at the other end of the spectrum of radiation, 10 to the minus 20 angstroms or minus 20 centimeters or something like that. Phenomenally short waves. And if you think about the Einstein's formula for the energy for the radiation in terms of the wavelength, hc by lambda or h nu, okay, you see that the electromagnetic radiation of radio waves has the lowest energy per photon, because the frequency is the smallest. The wavelength is the largest. So, if the wavelength is extremely large, c by lambda is extremely small. So, radio waves they are like tickling. They don't change. You don't notice them. Electricity, this light, you notice them. This is visible light. Okay. Now, go to cosmic rays. It's the maximum energy per photon. Therefore, do these things interact the same way with the atoms? Radio waves, when I say interaction of radiation with matter, it is still not complete. Exactly what kind of interactions? Radiation is time dependent. And radiation has many different frequencies, many orders of different frequencies, starting from radio waves, then you have microwaves, then you have infrared light, infrared waves, then you have visible waves, light, and then you have X-rays, then you have gamma rays, and then you have cosmic rays. So many different types. So each one does not interact with matter the same way. Therefore, the whole field of spectroscopy, you can see that if you take the same molecule, for example, benzene, send in a radio wave to benzene, and at the same time also in another molecule of benzene send in cosmic rays. Benzene reacts in different ways to that. Therefore, if the radiation is interacting with the molecule, the nature of interaction depends on the wavelength or the frequency of the radiation. And therefore, we have different spectroscopy branches. The X-ray photoelectron spectroscopy that Rangarav talked to you about is in the X-ray domain. Frequency domain is very, very large. Wavelength is extremely short. X-rays typically have wavelengths close to the spacing of the lattice points, crystal. That's why you have X-ray diffraction coming in. Crystals diffract X-rays because the spacings between the lattice points in the crystal are very close, of the same order of magnitude as the wavelength of the X-rays. So, different light, different electromagnetic radiations interact with matter in different ways. Now, radio waves largely affect the nuclei, and through the interaction of the magnetic field with the magnetic component of the molecule. Visible light has electric field, oscillating electric field, that interacts with molecules which are oscillating electric moments in the molecule. So you have heard of dipole moments for molecules, if you think about it, right? So when you write a molecule like HCl, we say that the charge centers, the positive and the negative charge centers don't coincide, right? It's not in the middle. The positive center is close to the hydrogen atom and the negative center is close to the chlorine atom. Therefore, if you put a delta plus here and a delta minus here, there is a dipole, which you write like this. Okay, what is the dipole doing? The dipole is not static. The dipole is oscillating. The molecule HCl is oscillating about its equilibrium position at any temperature above, including 0 Kelvin, sorry, not above, including 0 Kelvin, the molecule is oscillating. Therefore, the dipole is changing. The magnitude of the dipole is changing if the bond length is changing, right? What is the dipole moment? The bond length multiplied by the charge, delta plus or delta minus. Therefore, if the bond length is changing, the mu is time dependent. We call mu the dipole moment, okay? Is d times delta, where delta is either plus or minus. So that's the moment, and that is measured in some units, fundamental units. But the point is, the dipole is not static. The dipole is oscillating. Now, if the oscillating frequency of this dipole matches with the oscillating frequency of the electric field, please remember that's an electric field oscillation. That electric field oscillation, if it matches with the electric field oscillation of the electric field of the electromagnetic radiation, it's possible that the two will get together in resonance and transfer energy from one mode to the other. Therefore, the electric component of the electromagnetic radiation always interacts with the oscillating electric moment in a molecule. That's how we study. The magnetic component, perpendicular to that, interacts with the magnetic moments which are present in the nuclei in atoms and molecules, and the magnetic moment interaction leads to the radiation absorption or emission, but it's a magnetic component interacting with the magnetic moment. The electric field does not interact with the magnetic moment. The magnetic field does not interact with the electric moment. Okay, they are complementary. Yes, yeah. Electric field will interact with the oscillating dipole moment. Okay. So, the dipole moment is due to the HCl moving around about its equilibrium. So, if the radiation has the same oscillation frequency as this dipole oscillation, the dipole can actually absorb the radiation. Okay? Therefore, it changes the molecular nature. So, the radiation impacts, it changes the energy levels of the molecule HCl. Okay? So, when you say that it emits radiation or it absorbs radiation, what does it do? It absorbs radiation, for example, to go up from one energy level to another energy level. So if the molecule is oscillating at a frequency, say 2300 centimeter inverse, one vibrational frequency, okay? Now, if I put in a radiation which is 2300 centimeter inverse, it's possible that the molecule absorbs this energy and the HCl molecule goes to the next energy state, which is probably at 4600 centimeter inverse, something less than that. There is a 0-point energy to take care of. But the point is, it goes to the next energy level. It doesn't stay at that energy level because that's not its thermal equilibrium energy. It's an excited state. So after some time, what does it do? It tries to emit that excess energy and come back to the ground state. But that energy gets distributed in all directions. You can't measure that. You see that the energy is absorbed or emitted, provided you are able to see it in one direction. Okay? And so, to answer the question, the HCl molecule, if the radiation frequency is that of the oscillating frequency of the HCl, it's possible that the electric field will be absorbed by the electric moment. But the point is, the magnetic field, which is also oscillating at the same frequency, does not have a resonating magnetic moment at that frequency. The frequency of the magnetic moment resonance is much, much lower. Therefore, you want to excite the magnetic component of HCl. Yeah, go ahead.
I meant if the molecule didn't have a dipole moment, say it was a H2
Okay,
molecule.
if the particle doesn't have a dipole moment, I agree. This particular, for example, HH. Okay, there is no dipole moment. Therefore, infrared radiation will not excite this. No. To get the excitation, you see that the electrons have to go up. You can actually see the infrared light that is corresponding to the HH vibration. You can see absorption, but not through this kind of absorption emission radiation. You can see it by another method which was complementary to the absorption spectroscopy and was developed by Sir C.V. Raman, and it's called the scattering spectroscopy. In scattering spectroscopy, you can see the oscillations of the hydrogen, where the dipole moment is zero. Okay? So molecules which have a dipole, no dipole moment, permanent dipole moment, diatomic molecules, which have no permanent dipole moment, cannot be seen by absorption emission spectroscopy, but can be seen by a method which was invented by Raman in 1928 and for which eventually he won the Nobel Prize. Okay? So, but that's not the case with, for example, CH4. This also doesn't have a dipole moment. Okay? But the point is, CH4 doesn't have one oscillatory mode. It has multiple 5 atoms. 5 atoms together have 9 different types of oscillations possible. That's called vibrational normal modes possible for that. I mean, like your harmonic oscillator. CH4 consists of 9 harmonic oscillators in which the atoms are moving in different ways. Maybe next class I'll bring my laptop and I'll show you what are those 9 different oscillation modes. Physically, pictorially you can see that. That 9 different oscillation modes tell you that in some of these oscillations the dipole moment may be created and may be destroyed. For example, carbon dioxide. Yes, that's an easy example to write down. Okay? So let me tell you what happens in carbon dioxide. It does not have a dipole moment. Okay? There is no dipole moment. The charge center, the positive charge center and the negative charge centers coincide. But the point is, carbon dioxide has 4 different vibrational possibilities. One possibility is carbon, this oxygen gets extended, this oxygen also gets extended, therefore the oscillations are like this, stretch and compress, stretch and compress. But in that process, still you don't get a dipole because symmetrically both the oxygens are at the same distance from the carbon, no matter how far they are, therefore there is no dipole. So this cannot be seen by this emission absorption spectroscopy. On the other hand, if you have a carbon dioxide in which one of the oxygen atom bond length is shortened, The other oxygen bond length is this one. So it's an asymmetric form of stretching. This is a symmetric stretching. The asymmetric form of stretching, you can see clearly that there is a dipole moment during the stretching. And the dipole moment goes to zero when carbon dioxide goes back to this configuration. And it gets formed again when the stretching happens asymmetrically. So you could see that one bond is shortened, the other bond is lengthened. You can see that there are two dipoles and these dipoles don't cancel. Therefore, this mode can be seen by. So molecules which don't have a dipole moment do not have a spectrum, IR, that is radiation vibration spectrum, if they are diatomic molecules. Not if they are triatomic, polyatomic and many other atoms. And there is also a bending moment where this bond goes like this. That is, what is happening is, it is like this, but the bending mode is this and the carbon goes up. So it bends like this, okay? But the bending mode is twice degenerate, 2 times, because this is one way of bending, the other way of bending is this way. This way bending and bending in, bending out, bending in, okay? Bending out and bending in. So that mode is twice degenerate, doubly degenerate. And that mode also has a dipole moment, because the moment the oxygens are like this, you see there is a CO dipole this way, the two vectors add up to give you a total vector this way in the middle. One dipole vector is like this, another dipole vector is like this, and therefore there is a net dipole vector if you add the two. So this mode is also seen. Therefore, molecular nature is that molecules keep oscillating about their equilibrium and are perfect targets for understanding their structures through spectroscopic means. Anyway, in all of this, I never talked about the electrons. But if you shine visible light or ultraviolet light, the electrons may jump from one of the energy levels to another energy level. So you can have electron spectroscopy, electronic spectroscopy. Then the carbon dioxide, let's not take the carbon dioxide, let's take HCl. Suppose HCl rotates about the center of mass somewhere here, okay? Rotates about this. Which way does it rotate? About this axis means it should rotate in this way, perpendicular. If HCl rotates, you see that the dipole moment is the electric field is also rotating. A rotating dipole moment is equivalent to an oscillating dipole moment. But the rotational frequency is much lower than the frequency of the oscillation. Therefore, the rotational motion can be detected using microwave spectroscopy, not by infrared spectroscopy. Okay? So molecules have rotations, molecules have vibrations, molecules have electronic energy absorption, and molecules have atoms which have magnetic moments, and therefore their magnetic properties can be studied. And if this is not sufficient, the magnetic property and the electronic property, the electric property can actually also interact with each other, leading to what is called the coupling between molecular rotations and molecular magnetic moments. So all kinds of things. Therefore, when you say interaction of radiation with matter, it means infinitely many different things. But that's the definition of what you call a one-line definition of spectroscopy. Now, if you look at the spectroscopy, the radio waves usually affect the magnetic moments of the nuclei, hydrogen or chlorine. Now, nuclei have magnetic moments. The electrons have magnetic moments, all of you know that, because electron has a spin and a half, and the spin and a half leads to a magnetic moment for the electron. And likewise, proton is a spin and a half. Proton has a magnetic moment. Approximately, the magnetic moment is gamma J, the angular momentum of the electron. And what is this gamma? This is known in physics as gyromagnetic ratio. Roughly, it is EH by 2 mc. H is Planck's constant, E is the electric charge on the nucleus, 2 m is the mass of the nucleus c is the speed of light, roughly. And there is some degeneracy factor here, there is a factor. And so, point is that the magnetic moment is roughly proportional to 1 by m. Therefore, the electron magnetic moment is much, much bigger than the proton magnetic moment, because the mass of the electron is 1800 times less than the mass of proton. Therefore, you see that electron magnetic moments are much, much more significant. When you have a magnetic moment, mu, and if you place this in a magnetic field, H, what happens? The magnetic moment interacts with H. What is that interaction energy? That interaction energy